Okay, this is me working through an example of using the formal definition of derivative to find the derivative of this function, 5x squared plus x plus 100. All right, from the formal definition, I know I'm going to need that portion, and it's tedious algebra or fun algebra, but it's algebra that you have to be very careful about. So I calculated it by plugging in x plus delta x into this equation here. So you can stop the video, make sure you understand all the nuances of how I got to this last line. Okay, then I know for the numerator, which is the change in y over change in x, for the secant line, well, that's a change in the y values. I'm going to need this thing that I got up here, that I simplified up there, minus g of x. Notice that's the original g of x. Okay, so you can stop the video, make sure you get this. And here's where people screw up. That subtract, I'm subtracting everything. So the subtract works through. It takes the opposite of every sign inside. The opposite of every sign inside. So here's this without parentheses. You'll notice there's 3 common terms in this situation. And that's the final expression. So this is equal to this. That's going to be my numerator. All right. So the prep work is done, and this is what I really need. The derivative of g prime of x, is equal to, as that gap's getting really smaller, the slope of the secant line, this whole thing is going to be the slope of the tangent line. All right, so I don't really need to write this, but I want to make sure that you understand what that's happening. So remember, I'd simplified this from the other page down here. Yeah, so that's the change in the y's over the change in the x's. And then I factored out a delta x. So stop the video whenever you need to. I cancel the delta x because multiply, divide by the same thing. As with limits, you're always trying to plug stuff in. I could have even tried to plug, where's the beginning? I could have tried to plug it in the beginning, but notice every term has a delta x. So it's going to be 0 over 0. So I just saved myself some ink. So I plug in, I get 0, that's the derivative. That's the derivative. This is an expression for every single slope at every x value. Yeah, so if I want to know for this original function, hey, what's the instantaneous rate of change at x equals 1? I plug a 1 in here, and the instantaneous rate of change is 11. All right, see you in class.